brief summary of the last couple of videos. F13 is our usual vector. Delta S is the displacement vector. 9.5 centimeters times I, 10.5 centimeters times J. Now this was related to the F12 force vector that we looked at previously and actually dotted with the F13 vector. But that's not relevant anymore. We're just thinking about this force acting through this displacement. And if a force in this direction acts through a displacement in this direction, that force is always going to be, as we displace from here to here, that force is always going to have a component in this direction. And if we multiply just the component in this direction with the distance through which we do the work, we get the we get the magnitude of the work done. And if the angle is less than 90 degrees, that dot product and that work is positive. If theta is greater than 90 degrees, it's negative, because then we would be pulling back somewhat against the direction of our displacement. Now that's a physics concept that we don't expect to master right now, but it's the reason we do this. And we want to illustrate, again, the dot product, and later we'll use this idea of the dot product to better understand work and energy. So F13 dot delta S is the energy expended or work done by the force F13 if it acts through the displacement delta S. And that's always going to be the case for a force and a displacement. And that would be a constant force and a constant displacement. You'll learn in multivariable calculus, if you take it, how to do a line integral. We're not going to talk too much about that in this course. Okay, so, well, just taking these two vectors, we easily calculate the dot product. We get 23 Newton centimeters. Now, I mentioned that or comment that a Newton centimeter is a unit of energy or work. It's an unnamed unit of energy or work because newtons is a unit in one system, the SI system, and centimeters is a unit that's not in the SI system. So there's no point in naming this unit, but it's still a unit of energy, whether it's named or not, whether it's in a consistent system or not. It can be converted into work in units in our SI system or in any other system that we prefer to use. Okay, and I'll just say that a Newton centimeter is equal to 1/100th of a Newton meter. And that reason for that is very simple. A meter is 100 centimeters, so a centimeter is 100th of a meter. So that this Newton centimeter is 0.01 Newton meters, and this Newton meter is a named unit. We call it the joule. So a Newton centimeter is 0.01 joule, so that this would be 0.23 joules. And that would be very useful if you were doing a lot of energy calculations in SI units. You'd have to know how to make that conversion, but it's very simple, and you certainly should understand that. You should understand that much right now, whether you really understand what work and energy are right now. Okay, well, projection. Now we're going to calculate the projection on delta S of our work. Okay, so of our force. So right here is our force, right here is our vector projection. There's a picture of it. It's going to turn out that if we multiply or take the dot product of this vector projection with our displacement, we get the same result as if we take the dot product of F13 with delta S, meaning that the only thing that contributes to the work done here is this component of this force. Okay, well, the projection is easily calculated, and I'm not going to explain all the details of that calculation. It's identical to calculations we've done before. This part of the calculation is this leg of the triangle with a plus or minus, depending whether theta is greater or less. Well, if theta is less, it's plus. If theta is less than 90 degrees, this is plus. If it's greater than 90 degrees, this part of the projection calculation is negative. And we just multiply that by delta S over magnitude of delta S, which is just a unit vector in the direction of delta S. We want to continually remind ourselves of what these things mean so we have a deeper understanding of the situation. Well, This just comes out to be 23 Newton centimeters, as we can easily calculate. This is the dot product. Dot product is 23 Newton centimeters. Magnitude of delta S, well, I'm approximating, it's 14 centimeters. Not exactly 14 centimeters, but it's what you get if you apply the Pythagorean theorem to delta S, and it's pretty close to 14 centimeters. So I'm getting a little fuzzy with the numbers here, but that's because I kind of expect you to repeat these calculations and correct them. And that's multiplied by delta S over the magnitude of delta S, and I should have had a vector here and a vector here. And we get the vector, our familiar 0.67, 0.74 unit vector. And now we multiply that by, well, this divided by this is 1.7 newtons. Multiplied by this, we get something like 1.14 newtons, 1.24 newtons. This is what we call our vector component of F13 in the direction of delta S. This is the projection vector. We also call it the vector component, and we give it a symbol, F13 parallel. Okay, and these parallel lines here mean parallel. We read that as F13 parallel. Okay, well, if we multiply F13 parallel by delta S, by the magnitude of F13 parallel times the magnitude of delta S, we get 24 Newton centimeters, which is the same as this, except I've got a little sloppy with the numbers here, and we also have round-off issues. Close enough, and if you do this precisely, everything comes out exactly equal. Well, other thing we can do is we can take the dot product of this projection vector with our delta S, and we get the same thing again. Easy to verify. So, where are we? Well, if theta is greater than 90 degrees, of course, I have a little caveat. Our result will be negative, and I haven't gone into detail about how we analyze that, but it comes out very simply. If we take the dot product of our projection with our delta S vector, which we did right here, we get the same thing within round-off error as we do if we do F13 dot delta S. Again, if done precisely, these come out exactly the same, and it's easy if you understand these quantities and these vectors and where they came from to understand why that has to be true. Also, if we the magnitude of our dot product is equal to the magnitude of our scalar projection, which is just how long this is, basically our 1.7 newtons, the magnitude of our projection vector, times the magnitude of our delta S, which is our 14 centimeters, and that's the calculation that we did up here. And then there's a picture that goes with this. Taking the dot product of our projection with our delta S means, well, here's our F13, here's our delta S, here's our vector projection. So the dot product of this with this gives us the same thing as the dot product of our original vector with our delta S. Original vector can be seen as having a component parallel to delta S and a component perpendicular to delta S. Well, our component parallel to delta S is the only one that matters in calculating F dot delta S, or in calculating the work. So we could just simply eliminate everything but that component. Looking a little sloppy and a little wet here, but we'll live with that. So really we just have this dotted with this. And that's a useful image to carry when you think about work.